Okay, so we're back to here to talk about heat transfer. I had to watch the video with the kids. They indicated that I did make a mistake, and yes, I did call the cold one the hot one, and we have had a debate about this, but now everything is set. But the main thing I want to show you there is, conduction. That feeling that we have of cold is actually our heat leaving our body. Heat leaving our body, going into something else because of that temperature gradient. And anytime there's a temperature gradient, there's going to be heat transfer. Now, everything in your room, if you go around and look at things in your room right now, and you were to take a thermometer and measure the temperature, everything is probably equalized pretty well. If your room is, here at the house, we're keeping it about 78 degrees Fahrenheit. Everything's going to be about 78. But yet, when I touch things, some are going to feel colder than others, depending on how my body is conducting the heat away from my body to that substance. So that's what we're going to be dealing with. So first, let's talk about conduction here. Conduction. And this was developed, this equation that I'm going to talk to you about was developed via observation. Okay? And what it is a diffusion of energy. Diffusion of energy. And this happens in solids. Now, it does happen in liquids and gases as well. There's always that diffusion of energy, but it's going to be aided by other things in liquids and gases. It's the main form. It's the only form that happens in solids. Okay, so let's look at a surface, a wall. Let's look at a one-dimensional surface. Okay, look at a 1D surface. And so here we go. Here's our 1D surface, and I'm going to put it here. And I'm going to say that my one side of my surface is going to be temperature 1, and the other side of my surface is going to be temperature 2. And I'm going to say that temperature 1 is going to be greater than temperature 2. If that's the case, we know that what's going to happen. There's a temperature gradient here. Temperature 1 is greater than temperature 2. So which direction does the heat travel? Well, he's traveling from hot to cold, so it's going to go this direction in the wall. This is the direction of my heat transfer. Okay? And I'm going to put a rate, because we talk about rates when we talk about here. So Q dot, and we're talking about this conductance going this direction. Heat will travel from 1 to 2. Now, let's look at and just develop this law, and it's called Fourier's law. Of conduction. So we want to figure out here what our rate of heat transfer is, Q dot conduction. Now I want you to pause the video. You don't have to, but I want you to pause the video and come up with what are some things that you think should be in this law. What things do we need to consider when we're talking about conduction? This is my opportunity. So here you pause. Pause. Okay. So hopefully you paused. If not, well, I can't force you to do that, I guess. But what are some things that you thought of? Well, the first thing that you need to know for conduction is there's got to be a delta T. There's got to be a delta T. So let's put that in that equation, and I'll put here delta T over here. Delta T. There's got to be a change in temperature for there to be conduction at all. Okay. What else? What else does there need to be for conduction? Well, it makes sense that the heat is going to be inversely proportional to the thickness of this solid here. So we have this distance x, okay, this delta x. If you have a really thick solid, it's not going to be as much conduction as you have a really thin solid. It's going to go through it really, really fast. And so we're going to say this is inversely proportional to delta x, okay? What's also going to be important here is that the area where we pass things through. If it's a big area or a small area, you're going to have more conduction in a big area and a smaller conduction in a smaller area. So we're going to put area here. This is actually the surface area, so I put AS. And then the main component that we have that we're going to be dealing with is going to be the thermal conductivity. And that's going to be a fancy K. We're going to draw this a fancy K, thermal conductivity. And you can find the thermal conductivity in your appendices. There's a table A19 I believe. Let me just go here and check to make sure. A19 A19 is going to give you the thermal conductivity of a bunch of substances. Okay, that's going to be in here. That's. Let me get this document camera back so I can work it. Get my ice cubes out of the way here, and let's go here to my document camera. Here's table A19. You can see it's a little blurry here. I need to make this a little bit closer. Thermal conductivity, K, is going to be in this last column and give you for some solids dealing with it. So that's where our thermal conductivity is. I both have them in English and in SI units. Okay, now this is talking to us about what's going on. Now I want to make sure that we know this thing, this area, the surface area. Surface area. You need to know the surface area of rectangles or cubes. You need to know the surface area of a cylinder. And you need to know the surface area of a sphere. You also need to know the volume of these things. I do not provide these on the equation sheet. I feel like you need to know, you should know these things already. Know the difference between circumference and surface area. Know the difference between all these different things, and so that you know where to go. This is important, and as an engineer, I expect you to know these things. So please have those memorized, and know they will not be on your equation sheet. So when we look at this and we write this out, this is going to be Q dot of conduction is going to be equal to the thermal conductivity. Let me write this here. Thermal conductivity the surface area, like we said here, and this is going to be the temperature. Delta T was always T2 minus T1 all over X2 minus X1. It's always final minus initial. Well, this is going to give us, this bottom here is going to give us a positive number, because we're going to go from 0 to, let's say, I don't know, 2 centimeters or something like that. We're always going to get a positive number. But our top is going to give us a negative number, because temperature 2 is always going to be less than temperature 1. It's going to give us a negative number. So this whole equation here is going to be negative. And so in order, we don't want to think about conduction as being negative, so we put a negative side out in front of this. The negative sign out in front of it helps flip the sign, so we can say, hey, the conduction is going in this direction, and that's going to be positive. But we have this negative sign here to indicate to flip the sign that we have in our delta T. Okay, so that is our equation here. Our equation that we have is going to be Q dot conduction is going to be equal to minus K A dt dx. This is on your equation sheet. This is what you need to memorize, or not need to memorize. This is what you need to understand about conduction. Now, the thermal conductivity is a property of a substance. When we look at this, you're going to say, hey, metals, each metal, iron has this thermal conductivity, plastic has this thermal conductivity, skin has this thermal conductivity. We know, we can look that up. It's a defined property of a substance. It's going to be given in SI. It's going to be given in watts per K, and this is going to be Kelvin, per meter, or in English engineering units, it's going to be given in BTUs, BTU hour per degree Rankine per inch. Okay, so BTU per hour is the same thing as watts here. We have an absolute temperature scale, Kelvin or Rankine, and inch. Now, remember back when I was talking about units of measure and I was talking about temperatures, I could also put this in watts per degree Celsius per meter. I could put this in BTU hours per degree Fahrenheit per inch, and they would be the same unit because there's the same step size in Celsius and in degrees Fahrenheit. This is a very important idea to understand. The same step size. So when I'm up here and I'm talking about T2 minus T1, T2 minus T1 is the same in Kelvin and degrees Celsius, and the same in degree Fahrenheit and degree Rankine. So note here, when you're trying to find out your delta T, and you have Kelvin in the denominator of your thermal conductivity, you don't have to convert it. You don't have to convert it. The delta T is the same in Celsius and Kelvin, and is the same as in Fahrenheit and Rankine. Now, it's not the same as in Fahrenheit and Celsius and Rankine and Kelvin, no. But this one's just the same, and this one it's the same. The difference is the same because it's the same step size. Now, if you don't want to get confused about this, always convert temperatures to absolute temperatures, put them in the equation, and you're good to go. Always say, I'm going to convert every temperature in this class to an absolute temperature, plug it in the equation, you're good to go. But note, if I give you 20 degrees Fahrenheit and it heats up or it goes from 20 degrees Fahrenheit to 10 degrees Fahrenheit, that delta T is 10 degrees. That's 10 degrees change in Fahrenheit and 10 degrees change in Rankine. Okay, I'm belaboring the point. I'm talking about it too much, but I want you to understand here. I'm going to write it down one more time. Delta T in degrees Celsius is equal to delta T in Kelvin. And delta T in degrees Fahrenheit is equal to delta T in degrees Rankine. Okay, I'm just trying my best to eliminate this confusion that happens with students. The conversions that happen here sometimes can cause you to get to a lot of trouble. Okay, so that is conduction. Pretty simple, straightforward. If you see a solid, you're going to deal with this equation.